It looks like there are new results for indirect transitions with change of momentum for holes. And since she's the only person who is able to do such calculations, I'm also very intrigued and curious to see not only the results but technical details.
I'm going to talk about photo-induced lifetimes of holes influenced by momentum dispersion in two silicon nanowires. So here is the outline. First I talk the context and challenge, then methodology, results, and finally conclusions. So many of slides I just borrowed from my previous talk. Here is the motivation. So we know silicon nanowires have unique properties such as one-dimensionality, high surface to volume ratio, and they are applicable in optoelectronic devices, lasers, solar cells. And so far, many properties of silicon nanowires have been studied with respect to diameters, growth orientations, morphologies, surface modifications, doping effects. But we are interested to non-radiative relaxation rate of holes now, because we studied already non-radiative relaxation rates and electron dynamics of electrons in these two silicon nanowires models. So in our previous research, we did electron hole dynamics of silicon nanowires with conserving momentum, electron dynamics without conserving momentum, now hole dynamics without conserving momentum. This hole relaxation is influenced by momentum dispersion because we know the electronic structure of any periodic solid depends on K dispersion. So here is the methodology, kind of I think everybody knows. We basically use this one electron.
In the middle, question to everyone. I don't know the answer, but in the first term for kinetic energy, should one, instead of just gradient squared, put gradient plus overall momentum, like nabla plus k in brackets and then square? It's not for immediate answer, it's just a seed of thought. Please continue.
So K is momentum. K is wave vector. Like nabla plus K, that K is
yes.
wave vector?
Yes. How to, because all solutions are found separately for each value of K point, right? So how does software knows which K point we are considering?
Okay. So we basically use the one electron constant equation, and here is the solution of this one, the bottom equation, and using this wave function we calculate the non-adiabatic couplings.
Upper part of the button should be a laser pointer. If you need laser pointer. Okay, maybe not.
Okay, so, and here it is the kind of schematic diagram how electronic part and nuclear part works. If the model is illuminated by light pulse, then electron, it should be not LOMO, it should be HOMO, like the valence band. Yeah, I'm sorry, it should be valence band. So electron are transferred from HOMO or valence band to conduction band and leaves the hole on the valence band. And
so you are
when electron,
so you are excluding the del. Why are you excluding the del k not equal to 0?
oh, a momentum is not conserved here.
But if momentum conserves,
Then
like
K
the
equals
coupling
K prime.
between I and Z at any given momentum, why are you excluding that one? Is it excluding or not conserve? I mean,
So your question about I and J.
no, my question is why del k not equal to 0? You was defining that coupling at a specific condition that del k not equal to 0.
Since K and K prime, they are not equal,
So what
so
about
their
if they are
difference is
equal?
0.
No,
It's not 0.
Javid is asking like, would you allow situations when K prime equals K?
Yeah,
So it's
Yeah,
maybe should
actually.
be some different mathematical symbol, like either equal or not equal.
Especially here it's we call indirect transition, but in the result section, the
Oh,
relaxation
okay.
rate includes direct, indirect, like
Oh,
momentum
so
consequence.
in this case you are only considering the indirect.
In this equation, but in my research, both are included. Right.
Can you explain that again? Because
This
you
one?
said that one should be HOMO and it's
This
yeah.
So when the model is when light pulse is applied to the model, then electron transfer from valence band to conduction band, right? And then electron comes back to the band edge from excited states. That's what it shows here.
So the photon comes in, it gets excited, then it relaxes.
Suppose this is excited state, LOMO plus 2, then when electron come back to the LOMO, then it emits photon, right?
No.
This can be
So
not
this electron
necessarily.
is coupled with the nuclear vibration.
Photon or phonon?
But here photon, right?
So
This one is electronic part, and the here phonon, nuclear.
So is a photon absorbed or emitted?
Photon first, when light pulse is applied to the model, then photon absorbed and
Yeah.
electron transferred from the valence band to the conduction band.
Yes.
And to the excited states, like LUMO plus whatever.
Sure.
And then it will come back to the LUMO, right?
Okay.
Those electrons will come back. When it come back, then electron will coupled with the nuclear vibration, right? Because the model is heated. Am I right?
Okay. So you're just explaining the process,
Yeah.
what goes on.
Mhm.
Okay.
Yeah,
So
what's going on?
because I thought Aaron, I think, had a presentation where it emits a photon from LUMO plus 1 to LUMO, and then another one. But, okay, so this
I'm
is
not sure
the normal.
it emits photon, but I'm sure that electron will couple to the nuclear vibration. Lattice vibration. Yeah.
So elementary process is emitting of a phonon,
Yes.
but since electronic system is in a thermal bath or distributed distribution, the transitions, emissions of phonons of different frequencies are possible. When averaging over all processes of such nature, one is obtaining relaxation.
Okay, then using those non-abiotic couplings, we can calculate the autocorrelation function, and using that autocorrelation function, we can calculate rates of transitions. And
So
using
Fourier transform of autocorrelation function makes it time independent.
Fourier transform this one, rates of time.
So this one depends on time, and then through Fourier transform and integration over time, the frequency comes here.
Yeah. And then using those rates of transitions, our red field tensors, can get red field tensors, and then from the red field tensors,
Something is missing?
so time evolution of density matrix, I don't see it.
I can be wrong with indices, but it comes here.
Yeah. Thank you. Okay.
And it is not seen because of the blocking.
I think everybody knows this steps. Now, this is the band structure. Javed might have questions on this. I know usually I have questions on band structure.
Half a year ago he had questions. Maybe he resolved them.
Okay, so here I used 16K points. Basically, I did this to prove that we can consider 4K points. So if you look at in this band structure with 16K points and with 4K points, we can see the structure of the bands are almost the same. So we stick with 4K points since if we take more than 4K points, then coupling will have so many coupling files. Already we have for each K point around 900 coupling files. Okay, so here is the so here we can see that if the nanowire model is under light pulse, then electron can travel from one K point to the same K point and one K point to the different K point. So here in this transition, momentum is conserved, and for this one momentum, MR means the momentum restricted and momentum unrestricted. So understood by arrow. So and so this is momentum restricted, since electron travels from same K point, one K point to the same K point, but this is momentum unrestricted, since momentum is not conserved here. And here, if we look at here, this is the valence band of silicon 100 model. So when electron travels from valence band to conduction band, electrons leave holes. So electron from higher energy level to travels from lower energy level. So hole travels from lower energy level to HOMO. Right? Yes.
So your right panel is zoom in of the 111.
Mm-hmm. Oh, right. Oh no, this is 100.
Huh?
Right panel for 100.
Okay.
Yeah, it seems like 410.
Mm-hmm.
So then,
Then-
in your panel A,
Mm-hmm.
is that luminescence, or is that phonon modes? Your RM and MR and RMU, the arrows, going from about negative 2.1 to 0.7. Is that luminescence or is that phonons?
That's not
I
a
don't-
hormone gap.
So it's non-radiative.
I think it's just an illustration to show that those
It's
two
kind of
Okay.
just
are
one, yeah. Okay.
So is this phonon or photon? I think none of them.
Phonon, non-radiative transitions. Dissipation of.
It is just how electron travels from valence band to conduction band after under light
Oh,
pulse.
wait,
Right?
can you point it by finger or?
No, he's
Are you
talking.
talking about the same thing or different?
No, he's
Panel
talking
A.
about the first figure, I guess,
Okay.
right?
You go from negative 2.1 to 0.7.
That's a gap.
So it's absorption.
absorption gap. Yeah.
Okay.
This is a homo
But
and lumo bending gap.
It says radiative transition.
No.
No?
R and U are abbreviated
For
process.
momentum restricted and unrestricted. But your top then says radiative transition. So is it photoluminescent? And if it is, are you actually...
Wait, let's try to figure out what it is.
No, I guess
Is
it's
it radiative excitation? Because arrows are all up.
so
No,
I
just
guess
let's interpret what is.
yeah, I guess she's trying to say that this is the band gap. So if the electron relax from LUMO to HOMO, that type of transition can be radiative transitions. And in the right figure, this is the zoom in image for the HOMO state. So it's kind of intra-band transitions.
So
Those are like just for non-radiative relaxations.
the arrows in panel A are photoluminescent.
No, this arrow indicating that just a gap. That could be a
How
radiative
electron
transition.
travels from valence band to conduction band
Yeah,
when light pulse is applied. That's
this is
what
a
it
schematic
means.
figure for.
Then I don't
Fine.
see how you're saying radiative transition.
Yeah, that is.
Because you're absorbing light, not...
This is so. So later on, we will study the relaxation rate.
Okay.
No, his confusion arises because the
This
arrow
try
in
to-
upward arrow. So what is the arrow indicating there?
I think this is for, since we are going to study, that's why we will use
Okay.
these figures for as a foundation of radiative transition.
Okay, so your plan is later to look at
Mhm. Yeah.
photoluminescence. Or
I
think, yeah.
I think
Relaxation
they're
rate for
competing
luminescence.
between photoluminescence and non-radiative relaxation. Just
Mhm,
look at
exactly.
like quantum York.
That confusion
Okay.
will be removed if you put the arrow in the both side arrow. That would be made more sense.
And I don't know. I feel like that's not what it is because
You are thinking ahead of events. You like show a strategic plan for next few months, a few years.
Okay.
Right now there is a photo, at least as it is shown, photo excitation and cooling of carriers,
Okay.
which can be followed by non-radiative or radiative recombination, which will enable to compute photoluminescence quantum yield.
Okay, so those arrows just show it's absorbing light.
Absorbing light. Yes.
Okay.
And your plan of photoluminescence quantum yield is natural and relatively quick for gamma point, but there are technical issues to do everything at once for multiple key points.
So, okay, in that case, I have another question. In this case, if it is absorption process, is it possible to change the momentum at absorption process or later on after? Does the electron can excite it to the different momentum or should be excited to the same momentum and then following processes can move to the different momentum? I'm just wondering, I'm not saying.
I think
I do not see immediately theorems or selection rules that would forbid it, but I have never seen such things.
I mean,
It's widely accepted approximation that momentum is not getting changed while
during the absorption
Yes.
process, yeah.
The only thing where it partially observed is 4-wave mixing in 3-pulse photon echo. When submits short pulses at different angles, and then the echo comes at another angle. This is, but it may be not because of the momentum of an electron in a solid, but this experiment is typically done for molecules, but just because of interference and diffraction of waves that are coming from different orientations.
And I have another question on the right side one. So what is this arrow indicating that is it possible momentum relaxation?
whole
Whole relaxation. So from the yellow line, it's relax. It's
yellow line is bent.
yeah. I mean, from that band is going to that momentum, and then you are showing the 3 line from that momentum point.
Oh, I can draw more lines because from
Yeah.
one point to another point.
Yeah, but one is going to the yellow line to the upper line, upper band, and that can go to the any momentum because that band is almost flat in energy.
Yeah, exactly. But I didn't just show it here.
No,
So,
that's
so let's-
I'm
Don't say
very
question.
lazy.
no,
Question of Javid, does do these dashed arrows show most probable pathways or just arbitrary pathways for general illustration?
No,
Arbitrary.
I'm just wondering that you're designing a methodology from here or not, because if you decided that it can be relaxed from only that momentum, then you can exclude
Not
that.
only.
In that case, okay. So this is just a schematic.
Yeah, schematic. Yeah. Okay. Any question about the previous figure? Probably I can explain more. So in the rightmost panel, when electron transferred from valence band to conduction band, electrons leave holes. So holes travel from low, like states below LOMO to states below HOMO to HOMO. Okay, and as Javed said, he had a question. So electrons can travel one point to any other K point, like in the same K point, any other different K points. Like it doesn't mean that these paths are only this what I have shown here. I just showed here a couple of them. And this figure is, we will need this figure for later on to explain the how I calculated the relaxation rate. So here it is just the two.
So the upper band shows like 5, 6, 7, 8. Is it because the HOMO is degenerate?
Yeah, because HOMO and HOMO minus 1 is like they are overlapping. So if I draw those two, then they are overlapping. There is no difference. I cannot identify, like I cannot take them separately. So I decided to use these two, HOMO minus 1 to HOMO minus 2.
So
It is just, it shows how, because for indirect transition, to calculate relaxation rate, so we need consider multiple 4K points here. And those states for 4K points we need to combine it in a single file. So this schematic diagram shows how the states for 4 different K points are arranged in a single file.
So
Yes,
I have maybe I'm reading it weird, but state 5 has k equals 0.5, but that point is above 0.
Yeah.
And then k, state 8 is k equals 0, and that's above 0.5. And then my second question is, how is HOMO minus 2 above HOMO minus 1? Because the occupied states should, if you go to lower states, should decrease in energy.
I'm listening to your question there.
I'm with you. I'm very intrigued to hear the answer.
So I don't get this figure. What is this doing?
So this is showing how each k point is assigned in a file, right? So in ours we have,
What is these two lines? This is two bands taken from previous one.
so
right?
like in our adiabatic coupling file, the diagonal is always 0 because that's I equals I.
No, I'm not talking about naming. I'm talking about this line. This two line is taken from the previous figure. Right?
Yeah.
Okay, so we considered 4K points. So for each K points, we have a file for bands, right? So we considered, I think, 30 states above LOMO and 30 states below HOMO. So the active window, like 60 states. So for each K points, we have 60 states. So if we consider momentum is conserved, then we can use them separately. But if we consider the momentum is not conserved, then we need to combine them together. So what we did, this is the single file which contains the states for each K point, like all K points.
So my question wasn't how you put in the file. My question is, on the figure,
Okay.
your k equals 0.5 is above 0.
So there is a suspicion that data in your file are correct, but the labels on the figure are swapped, like upside down.
So can you go
to the
back to
image
your figure?
file.
Okay, I'll go there, but I need to explain this one
No,
first.
that's a different. Yeah. that's
Okay,
a
so this one is HOMO
No,
for
it wasn't.
K.4. K.4 means K.4 is 0.5. So this is HOMO for K.4, HOMO for K.3, HOMO for K.2, and HOMO for K.1. So if I consider this one is number 1 state, 1, 2, 3, 4, and then 5. 5 is HOMO for K.4.
Okay, this is not a HOMO minus 1. This is a HOMO 1.
HOMO minus 1.
It's just a name. HOMO 1,
Five.
HOMO 2, HOMO 3.
5, state number 5 is HOMO minus 1.
Yes, I'm not arguing this at all.
Yeah, now this
I'm
figure.
saying on your figure,
Mm-hmm.
it seems like it's misleading because you say k equals 0.5. So if you go
Oh,
to state
okay.
5, it says k equals. What does it equal? 0.5. And then if you go down, it's 0. And then if you go to state 6, it says k equals 0.33.
Oh,
And if you go down,
yeah, I see.
it's not
Yeah.
that.
Mhm.
So that was my first question. What does that mean? And then my second question is, homo homo minus 1 is black, and that's lower in energy than homo minus 2, which, to my understanding, when you order the states, homo minus 1 should always have less energy, or be higher in energy than homo minus 2. Unless you're in like diabatic state and you're doing dynamics and then it flips back and forth.
Mhm.
But in this case, how do you get red on top of black?
Or it is a typo and one should label it otherwise, like red homo minus
Mhm.
1 and black homo minus 2.
Yeah, it is misleading. I understand that because I wrote k is 0.5, but on the x-axis it shows 0. Okay. I need to check this figure. Then. Any
Okay,
question?
what is the, I missed that one, I already stated that. What is the purpose of this image things? I mean, you
Which
got,
one? This
I mean,
one?
this, yeah, this figure.
It's just it's a technical thing, not any
So
science on it. How it's just explains how the states are arranged for calculating relaxation rates when momentum is not conserved.
Oh, okay. So it's not that just you are considering these two.
Oh no, it's just how the states are arranged.
Okay.
Yeah, I need to check this one. First I wrote state 5 is 0, but I think I need to check it. Okay, now since we considered 4 different K points, for each K points we calculated Redfield tensors, then K point. Yes, so first for each K points we calculated Redfield tensors, and then we have 4 Redfield tensors, 4 files, and then we combine those 4 files together. So, for K point 1 to K point 1, K point 1 to K point 2, K point 1 to K point 3, K point 1 to K point 4, and for other K points similarly. So we have 16 Redfield tensors files. And
Fatima,
mhm.
if you will present this again sometimes, would you be able to graphically represent it, like maybe like flow chart and blocks?
Yes. Okay, so I think I can talk about the Redfield tensors later on. Now, how to calculate Redfield tensors first? Actually, I was I'm talking ahead. So first, how Redfield tensors are calculated here. We need 3 things on the folder. Number 1, all coupling files. All coupling files means direct and indirect transitions. Direct means coupling files when momentum is not conserved, and indirect means when it includes momentum is conserved and not conserved, both, right? For indirect transitions,
Indirect, not conserved.
Okay, for direct momentum is not conserved, and for indirect momentum, for direct momentum is conserved, and for indirect momentum is not conserved. So all of these coupling files we should have on that folder. All files for states, like for 4 different K points, there should be 4 files which contains the states for each K points. And we need this MATLAB code number 3. As you can see, there are 2 names here.
It means
on the code.
you want to put someone responsible if code is not working.
It works. So all coupling files means so we need in order to calculate Redfield tensors we need these three kinds of files. Now I'm going to explain number one, all coupling files. So all coupling files means all coupling files include direct and indirect couplings files. So for direct couplings there are around 892 files here. For indirect couplings, it's the coupling between one orbital to another orbital. So it's a huge number. So for k.1 to k.1, 892 files. And for k.1 to k.2, 892 files. So there will be a couple of thousand files. Right? Yes. So 0k point to 0k point, for 0k point to 0 to 0, 892 files. For 0 to 1, 892 files. So all of them should be in that folder where we will calculate Redfield tensors. And number two, we need energy, like a file for states. So each energy, it's just a name. So each file for each k point have like maybe 60 states. And then number three, we need this MATLAB code. When we run this code, we should have Redfield tensors. So after running this code, we have 4 Redfield tensors. And then we need to calculate Redfield tensor 1 to Redfield tensor 2. Redfield tensor for 1 k point to Redfield tensor for k point 2. Redfield tensor k point 1 to Redfield tensor k point 3. And such like that. So we have 16 different Redfield tensors files. As here we see. And then we have another MATLAB code to superimpose them, and finally we have only one Redfield tensor, this 5R1 we have, and combining 4 energy profiles, we have the combined one. So finally for calculating indirect transitions, we will use these 2 files.
So you're putting small matrices as blocks for bigger matrices.
Mm-hmm. Yeah.
Okay. And you compose 4 indices into 2 super indices.
Yeah. Mm-hmm.
Okay.
So for dynamics calculations, these 2 files we should have, and this MATLAB code. So this MATLAB code and these 2 files should have. Any questions so far? I think no one understands.
It's so complicated that everyone already lost the steam to challenge these questions.
Okay. So I think I can go ahead.
You can, if you see no response, you can ask rhetoric question like, what is the goal, and why are we doing this way, and
Question
what
to the
is-
audience.
Well, you pretend that it is question to audience. No one will ask, so you ask question, then answer it yourself. But
So how do you get oscillator strengths between different K points? Is it still just the expectation value of the transition dipole operator?
What is that? Can I
So
please repeat?
with highest oscillator strength, Right, so I presume you have to get the oscillator strength between different K points. Right? So is the oscillator strength still the expectation value of the transition dipole operator squared times by constants? Or is there a different formula to get the oscillator strength?
To get the question, yes and no.
Yes? Then-
Yes, that equation that you verbally pronounced is correct. And no, that it is not between different K points. It is the same what Javid was asking about. Like other optical transitions with change of momentum.
Okay.
There is an approximation that momentum is not changed. So there are optical oscillator strengths are not assumed non-zero. One never checked whether it is right or wrong. That optical transitions occur only without change of momentum.
So I guess then my follow-up question would be, if it is an indirect band gap, how would you predict the oscillator strength?
The thing is here for indirect band gap is silicon 111. So it is not solved yet.
But
You
For
can take
1008 it is
same clip on.
totally solved. For
Yeah.
111
The
there is a problem.
The question is perfect.
so I know that Eric Hobby in silicon has indirect silicon
Indirect band gap.
band gap, but it still emits. Which then means that
What?
what?
Repeat. Everything was perfect until now. Repeat.
So Eric Hobby works with stuff and it's
Yeah,
indirect.
What is indirect?
The
Band gap is indirect.
Yeah,
Band
let's
gap.
let's challenge Levi right now. Silicon is indirect in which morphology?
I thought it was in nanoscale.
But what do you mean nanoscale?
So on the order of 10 to the negative 9 meters.
What shape? Which shape you mean?
I don't remember the details of this talk.
But roughly, you are thinking about confined structures.
Yeah, I thought it was spherical.
Okay, so you're talking about quantum dots, spherical.
Sure.
How do you use concept of momentum dispersion for confined nanostructures?
I don't know.
You
I know that you can't use it because the electron doesn't go through,
exactly.
but I don't remember all the details of his talk.
You you already told everything. So in confined structures, three-dimensional in like zero-dimensional objects and quantum dots, there is no momentum dispersion.
Sure.
You can tell it in public, and no one will
Yes.
kick you back. From
I don't remember the details, so.
So silicon is indirect gap material for non-confined structures, for bulk,
Sure.
thin films, or nanowires. Nanowires are easiest things, therefore Fatima is doing them. So only when there is a translational symmetry, one can speak about direct or indirect band gap. For three-dimensional confined, like zero-dimensional nano dots, concept of direct, indirect gap and momentum dispersion is not applicable.
So if we had a one-dimensional material,
Like nano
wires,
wire or carbon nanotube,
sure. Where was it indirect band gap?
it can be either direct or indirect,
Yes.
which
If
differs
the-
from material to material.
If the lowest emission state is indirect.
Then it will not emit.
So what if it's assisted by phonon modes?
Then typically you do research and check, but
Because
in majority of cases,
Okay.
indirect gap is responsible for not emitting materials.
Okay.
If you see indirect gap, you can stop and tell like
okay.
it's highly likely it will not emit.
Okay, so if there is a case where it is emissive via phonon-assisted emission, would it still just be the same K point, so you wouldn't have to worry about?
For non-assisted emission is more delicate process, which is of the lower probabilities, like second order or next order correction. Enough? Okay.
I'm sure that so far the procedure is not clear to audience. I think I can summarize like short briefly. So what here for calculating relaxation rate when momentum is conserved, we need we consider so we need a so if we consider momentum is conserved, then electron can or hole can travel from one K point to the same K point. And since we considered 4 different K points, so we can calculate the relaxation rate for the same K points. So in order to calculate the relaxation rate, we need first we need rate field tensor. For rate field tensor, for calculating rate field tensor, we need 3 things in the folder. Number 1, coupling files. Number 2, energy or files, which contains the states, and a MATLAB code. So we can calculate rate field tensor for 4 different K points. So we'll have 4 rate field tensors for 4 different K points. Now, since we are going to calculate the relaxation rate for indirect transition, so we need to correlate these 4 rate field tensors. So K point rate field tensor for K point 1 to rate field tensor for K point 2, K point 3, K point 4. So we need to combine them, correlate them. For combining them, we use a MATLAB code, which the output is 16 different rate field tensor files. So rate field tensor K point 1 to K point 2, K point 1 to K point 3, K point 1 to K point 4, K point 1 to K point 1, and similarly for rest of them. Like so 16.
So number of K points squared.
Yeah, 4 square, since we have 4 K points. Now, since we will calculate relaxation rate for indirect transition, we need to combine the 16 rate field tensors file to one single one, which is super tensor. So we combine them together, and we finally got these 2. Finally, we have this. Why I don't see this one. So this rate field tensor file contains all of them. And this file contains states for 4 K points. And this figure was about how the states are arranged in this one. So we have this finally this energy pop and this super rate field tensor. Now, question.
So you're only considering 2 states around the HOMO lookout, right?
No, that was just a schematic diagram. We considered I think 30 states below HOMO and 30 states for whole 30 states below HOMO. I just showed 2 states how the states are arranged in this file. So 1, 3, 4, 5, 6, 7, then again 5, 6, 7, 8, then 9, 10, 11, 12, and then 13, 14.
Each one of those red field tensor files contains information for 30 up and 30 down. All.
Mm-hmm. Mm-hmm. And for 4 K points, at 4 K points, to the same K point or to the same 1 K point to another. Once we have these 2 files, we can we need these 2 files and this MATLAB code for calculating electron dynamics. And for calculating electron dynamics, I considered interband transition with highest oscillator states for at each k point. This is just the portion of MATLAB code. Now here, this is the
And here was another image that is skipped, right?
exactly
In
yeah
the
yeah
your version.
yeah. So for
So you can verbally explain how it looks like.
plus 27. I just wrote it randomly. It's 27. Homo minus, suppose it's 20. So this is silicon 100. Now silicon 111. Long plus 15. And for this one, it is not solved yet. Here is zigzag. So now these are the dynamics figure. So electron hole relaxes from HOMO minus 20 to HOMO. Suppose this one for silicon 100. It is solved. So we can calculate the relaxation rate. For silicon 111, this relaxation rate, I'm not sure. I can calculate this relaxation rate, but I'm not sure whether they are correct or not, because I don't see this figure, like clear figure here.
Can it be related with error in counting order of orbitals that I was?
Yeah, probably. I need to check that. But for this one, for 100, they're the same. The arrangement is same. So it worked for that one, but it gives relaxation rate. Some values are like
And what
looks
are,
like
the,
they're
what are
unrealistic.
the axes in your schematic diagram? Axis, x-axis and y-axis.
Here,
Yes.
this is the log 10 time. This is energy.
Time.
This is time.
X is time and y is energy.
Yeah.
So in making these diagrams, you are
Energy. Yeah. It's
Energy.
something related to the
you're
energy of the states.
averaging over all k points. Although you're computing them, here if you do such diagrams, the change of momentum is hidden, is not explicitly shown. Okay. And what is the main observable that you are targeting?
Relaxation rate.
How does it look like on these diagrams? How these diagrams that you sketch by hand correlate with the relaxation rate? Can you point it out on the diagram?
Relaxation rate.
Or relaxation time?
Time, how long it takes to relaxes from LUMO plus 15 to LUMO, or HOMO minus 20 to HOMO.
Okay,
Right.
but the time or rate is just one number. What is this number on the diagram?
In this diagram,
Yes.
I don't remember.
No, just show here. Anyone wants to help?
You're looking for the rate or the relaxation time?
Relaxation time.
That would be where it flattens out again at the end.
Or well, there is an equation how to get it, but the point where it changes most abruptly, like midway in this transition. Okay, so like here, therefore electrons to holes.
Okay. Yeah.
Right?
So So for silicon 111, this holds relaxation rate for holes are not solved yet. Otherwise, everything fine. Now I need to go back to the slide.
Computer.
Okay, so this table for silicon 100, everything is okay here.
Either skip it or explain how to read this table because it's a lot
Ah,
of number.
yeah.
Well, if you tell that everything is okay, probably it is sufficient.
So first column is value of key points, since I considered 4 key points here. And then second column is band number of states. I consider this number of states because they are with highest oscillator strengths. For each key point, I consider 10 states. 10 states with highest oscillator strength and interband transition, not intra. And then this is the energy difference between this state to the HOMO and this state to the HOMO. The energy difference between this state to HOMO and this state to HOMO, like every states and HOMO. And then these 4 columns for all transitions means it includes direct and indirect transitions. And this one, momentum restricted transitions, only direct transitions. These 4 columns. I included them because I need to compare how rates are behaving when momentum is restricted and when all of restricted plus non-restricted.
Are you going to visualize this table in some graphical form?
Hello?
Graphical. Are you going to plot some data from this table?
Mm-hmm. Yeah, these data are plotted at around. Okay, these data are plotted. So this is the initial state. This is relaxation rate, and then the inverse of relaxation rate is time, and this is the natural logarithm.
What is the initial state number?
For calculating relaxation rate, we need to consider the initial states for electron and hole.
And then what is the band number then? Suppose like for HOMO minus 18, that means it's like,
So suppose this one, it is at K.0.33, this is the like HOMO minus 29. Okay, and this HOMO minus 29 is 118 in that combined state file.
okay, got
Okay,
it.
and this is in the separate
Okay, got it.
file of states like energy profile. So these are numbers are on that big one file,
Okay.
which contains states for 4 different K points, and these numbers are just a number of states in individual file for states.
So you suggest to call HOMO minus 1 bands, then K points, and when you combine both numbers into one super index, it will be state. Right?
So that's the number from your calculation setup, not from the.
And this is for silicon 111. Here we can see, as I mentioned earlier, that whole relaxation rate from HOMO minus something to HOMO.
Well, if
not solved
you
yet.
spend enough time and focus on the data, probably you can see, but not in the short time, right?
Yeah.
Okay, so I think some unrealistic values here. Suppose here 209.
So
I
why
don't
you
think
thinking
it's
is
right.
unrealistic?
Yeah, and here negative 11.
No, I'm just wondering why you thinking this unrealistic and
I
someone
don't think it should be
realistic.
209, right? I don't see this kind of
209
values.
in which units?
Oh,
It's
there is
a
some
rate,
experimental.
it's an inverse picosecond.
Huh?
Inverse picosecond.
Inverse picosecond? So it's too quick. Right?
Is it too quick? Yeah, too quick. Yeah. Kind of.
So it is expected to be like 1 inverse picosecond intuitively, and it is like 2 orders of magnitude quicker, which induces suspicion.
I don't see this big value for relaxation rate so far. So and negative values. Even I don't see. So first time since I saw it,
So for
I thought those are.
111, probably there is some bug in the code or in the way
Mhm. Yeah, probably
States
the
are-
arrangement of that states. That Levi
Do you have
mentioned.
any experimental results, similar system on this one? Or any experimental result to compare this one, how you? No, it seems like you are comparing exactly, I mean, that one, I'm just.
I saw some papers when people experimentally find dispersion curves, but for momentum dispersion rates, I'm not sure if it is possible at all.
Mhm.
So, maybe we can get some integrated rate, and if it will, and then compare to
Mhm.
experiment. If anyone will find a way to directly compare this data with experiment, it will be worth of just.
Yeah, I have no idea what number is realistic, that's I'm just wondering
I think
what value is.
any relaxation we compute like cooling of a carrier within like 300 femtoseconds. It's,
Mhm.
there is an observation that in a lot of systems, the rate of cooling is the same. Like you change material and you get approximately the same rate of cooling. Maybe twice as or bigger.
Mhm.
If it differs 2 orders of magnitude, it is a little suspicious.
And since this one is not doesn't look good,
So you have some noise
that's why
in the expectation value
those
of energy.
values might be
Okay.
something is wrong with them, since this figure is not correct.
But you follow the same methodology, right?
Yeah. Yeah, but it has indirect band gap. Silicon 111.
So it is a method that works only for direct band gap by now.
I need to check. I need to work on more.
It would be a good idea to investigate, you know.
Now these are the figures, like graphs for those big tables.
And this is for the nanowire which looks reliable, right? 100.
Yeah, this is reliable. Silicon 100. I did not feed this data yet.
But
So
can you briefly explain? What
yeah,
what
so
it
for
is?
these are for indirect transitions, and those are for direct transitions. Here momentum is constant, and momentum is not constant. So this
So lower the empty symbols.
constant plus not constant, both.
Okay.
Like all transitions, all includes momentum restricted and unrestricted.
So time is shorter if you include all.
Yeah. So if we consider the momentum restricted and unrestricted both, then the whole relaxes shorter, since there are multiple pathways to relax.
And here that are data only for holes.
Yeah. These are for holes for all transitions, like both momentum restricted and unrestricted, and those for momentum restricted.
What was it?
So are you saying your legend is wrong?
Which one? No, this one is okay. 100 is okay.
You have hexagons that are open and there it says restricted, and you said it was their all.
Yeah, you said opposite and indicating the difference.
Ah,
Yeah, this.
yeah. This is wrong. This one should be wrong, and this one should be momentum restricted.
So it's an easy fix, just so.
Yeah.
So there are both these long escalations.
David, were you going to ask the same question?
Thanks.
And Jared?
Okay, so finally is like all is open one, is it?
Yeah. And this is the logarithm. Natural log.
So then I'm just wondering if you included both restriction and unrestricted, why is
Why quicker?
relaxing slower? No,
Slower,
sorry.
quicker. Time is shorter.
Quicker, sorry, yeah. Okay.
So then probably I need to.
No, I got it. Sorry,
Can
my
I
mistake.
explain if you still have this question? If you have a plastic bottle with water and you have like a drill, you drill it once, it will deteriorate with one speed. If you do it several times, it will.
Yeah, first, yeah. No, I'm just got confused with the reason.
Oh, that's why I showed a figure like a non-radiative transition. Then hole can transfer from one K point to different K points. Okay, I'm talking about this. Here, this right channel. So we can see a hole can relaxes. If it is momentum restricted, then just this way. If momentum, all transitions, then a hole can relaxes this way, this way, this way. So not be pathways.
And half year ago, Javet was suggesting to normalize this data.
Yeah.
Divide by number of channels.
Oh, so did you?
No.
Wait for another half year.
Questions?
So for the momentum restricted, the vertical,
Mhm.
do you not need four times relaxation times for each K point? What does it mean to just have one time for restricted?
One times.
Like if you go to the last plot, the one you just were at,
The sum of population of whole all momentum points
just independent.
equal to one, non-independent.
Oh,
Is
we
each
have
one
four
she's
set of
using
data, right?
Some of this already.
See, we have four set of data for each K point, right? Is,
Oh, just kidding, there is
for each
something.
K point.
Yeah.
So they differ by color.
Mhm.
Yep.
So that K point is indicating that your initial state, right? Initial momentum of the, not the final
But
state.
now,
Then
initial or
If
final?
it is
It's a number of.
if it's not, if in all cases,
Wait. Yeah, the question makes sense.
Which question?
I mean that K point is that K equal to 0. That means this is the momentum at initial state, right? Because if your momentum doesn't conserve, the final state is going, it's maybe on the different momentum, not in the zero momentum.
Mhm.
So this momentum is why are you starting the calculations?
So this means K0 means electron is the hole is traveling through the same channel.
What about in non-restricted case?
It can go to
Battery-
another
batteries.
channel.
Another one, so it's not in a zero anymore.
Oh, this is just gamma point, K point.
Final state.
So
Is
this,
it missing something?
here it's just the initial condition.
Yeah, that's what I'm saying.
Yeah, it's just the initial
This,
condition.
this is just initial condition.
I'm not sure about initial.
So when
Like
you say
I-
that K equals 0, you're just saying that you're starting at K equals 0 and it ends up
Oh
going wherever.
no, those are K points. So I considered 4 K points, right?
Yeah.
0, 0.16, 0.33, and 0.5.
Okay.
This is just K point.
Yeah, but K point of what? In which case?
Which case means?
So I
In your
guess it's
unrestricted
initial, yeah.
case, you're not requiring that K is fixed. So is the K that you're claiming up there, is that the initial K or is that like the final K?
So is this K equal to 0? That means that hole at K equal to 0 when time T equal to 0. Is it? Am I right?
No, hole should be at the same K point always.
No, I mean
Final
at
is-
the initial state when time T equal to 0.
Electron or hole at K equals 0. And
Zero.
finally also K equals 0.
In restricted case.
In restricted case, yeah.
What about in non-restricted case?
In non-restricted
It
case,
can
we
be
don't know.
anywhere.
Anywhere, yeah.
So is it, this is the initial condition of
Oh,
hole.
exactly, yeah. Initially.
Yeah.
That makes sense now.
I have another question about that actually. Do you know why you're getting shorter relaxation times for higher dissipation energies? 'Cause that strikes me as odd, I guess. So if it has farther to relax, it relaxes in a shorter amount of time, which seems strange.
It's a energy gap.
Okay. Please try to answer. Several of us were already answering this question.
Wait, what?
Several of us were answering this question while fighting with reviewers.
Oh. So, I guess, do you Why do you suspect that your relaxation time goes down as your dissipated energy goes up?
So it needs electron or hole needs to travel multiple states.
Mm-hmm. Makes sense?
If they are close to LUMO or HOMO, so they don't need to travel so many states, right? They can relax quicker.
Wouldn't that mean that you have shorter relaxation times for lower dissipated energies, though?
What's the definition of dissipated energy?
That's another legitimate question. What is on the x-axis?
The energy difference between the HOMO and the state from where hole is traveling to the LUMO.
Then it should be.
So like energy
cost-
difference between HOMO minus 5 and HOMO.
How much energy was lost to heat specifically?
Mm-hmm. Mm-hmm. So the question of London was like if one would apply such analysis to two-level system, just two quantum levels, and look how the rate of relaxation from one level to another level will depend on the offset of energy. Then one would
Yeah.
expect that at smaller energy it would better fit resonance condition and dissipate quicker.
Yeah.
If you make it bigger offset, it will slow down.
Yes.
And here dissipated energy increases and the time gets shorter and shorter, gets quicker and quicker. You already answered correctly. I'm just not sure if Lyndon bought this answer.
Yeah, I guess I didn't follow it.
So, so again, I have a confusion about dissipation energy in this case. Is it dissipation energy is the energy and range by considering they calculate the relaxation time?
Please repeat.
I mean, so relaxation time is like, if we define the relaxation time is DDE of something. Let me make my idea clear first. I have some confusion on that. So this dissipation energy is indicating that initial and final is energy difference, and the required time of that is relaxation time.
Mm-hmm. Yes. Let's get back to London to make him happy. So I'll just translate Fatima's answer in finger language. So if you have two levels with different offset, you have resonance condition, or what I've learned it from Yun and his experimental advisor many years ago. They call it gap law. With the gap, what it's called. But if between there are more states, there are resonance transition to subsequent levels, it can get quicker because offset between them is much smaller. And if you increase it further, larger number of states is in between, and there are transitions through multiple channels in parallel.
Well, I guess I can see how the rate would be quicker, but it still seems that it should take longer because you still have farther to go.
You cannot answer it philosophically in general. It differs from system to system.
Yeah.
It strongly depends on the density of states. For
Okay.
denser states, it is what Fatima is showing.
Mhm.
For sparser, it will follow your original.
And also another thing is not a continuous process, so more energy changes doesn't mean that it takes longer time.
Because your density states usually gets denser the further into the band you get.
Yeah.
So you have increasing numbers, so your number of transition states doesn't stay constant, or doesn't scale linearly. So for like one dissipated energy, you could have like 10 possible transitions.
Yeah.
As an example, but if you go to 2 eV, you could have 100.
Okay.
So then that's gonna parallelize that more.
Okay.
So I have one little bit different, not a question actually, I just wanted to know. So if we excluded 3 points from this graph, 2 red and 1 magenta color, is the relaxation rate is kind of independent of the momentum, initial momentum points. What is the significance of that?
So for K.0 for gamma point, I don't see.
I would ask
linear.
well, differently. Is it for momentum restricted data, the relaxation time as function of dissipated energy looks like a constant? Is it a general observation for any nanowire, or it is just a coincidence for this direction?
It's not general. Like when I consider the first 10 states above and 10 states below HOMO, then I think it's different, the trend. Here I consider the 10 states with high oscillator strength. I don't know, I'm not sure. It's check again.
So maybe there have some difference in the band structure. and that
Maybe, or maybe,
introduce-
I don't know, I don't remember.
Maybe there is
now.
something
Some special feature,
specific
yeah.
for this exact symmetry
Mm.
that facilitate this result, but I doubt that it can be generalized for any material in any crystallographic result.
Okay, next one. Now,
So there is a-
these rates, like open,
And
The
those are
symbols?
doubtful.
those are
results.
doubtful, yeah. And those are solid symbols, those are good. Here we don't see the trend is,
So
the slope
doubtful,
is zero.
doubtful for empty one, not the solid one, right?
Solid ones are good.
Solid one is good.
And the labeling is
Again, here the symbol is different, like flipped.
like when you see all, you need to read MR.
Yes.
When you read MR, you need to understand all. Okay.
Any question here? I don't think I need to explain this.
So what is the feature of these two cap points given two different trend on the solid line? I'm just trying to figure out what is the reason. Because one is increasing, one is decreasing, and they met at the same point at 2.
For two points increasing and two points decreasing for momentum restricted, and for all transitions those are not like, those are not good data. They are not perfect yet.
One probably can find explanation for this correlation if it is correct and if it is needed by looking at this data and density of states found separate for each K point. Maybe for those that decrease, the density would become denser as you go to higher energy, and for opposite, for another two, density will become sparser. But one can dig so deep. I'm not sure how important it is.
Or maybe they have a sub gap initially up to 0 to 0.25.
There is something.
And then after that, it's showing that there is sub gap, but then it's become more continuous.
Mm-hmm.
Okay. Oh, you have question.
On the previous plot that goes to that one.
No matter what.
So you said haven't fit it yet. What are you going to fit it to? Like a single exponential or a double exponential?
A linear? Looks like they're linear, right?
Oh, yeah, so this was a log.
So then it will be exponential if, but
conclusion is the indirect transition is always quicker than direct transition since there are additional channels.
Javid may become picky, and he wanted to hear that indirect plus direct is always quicker
All
than
transitions,
direct
I mean.
one.
Yeah, I guess that should be the right term.
Yeah, and gap flow works differently for different key points, as you already. So, and thanks.
Okay, let's thank Fatima for.
So I'm just wondering why you calculate all transition rather than calculating direct and indirect.
To
Ultimately,
avoid
all,
your questions.
Because all is always supposed to be quicker than only restricted case, is it? Or because all means is including direct and indirect. So if we consider the both relaxation pathway is supposed to be quicker than if we put some condition on the restriction on there. In usual sense, I mean.
I don't know, maybe Fatima has different answer. My answer is it is developing of the code.
Okay.
So for direct it is so much easier.
Okay.
And
Yeah.
then
Yeah.
there is a
that
reference
makes-
point.
yeah. Okay.
I don't have any answer. Any other question?
More questions one, more questions two, more questions three. Let's thank Fatima once again. Well, maybe there will be volunteers to present during the break period, but I'm not aware of them yet. So, thanks much for supporting activity during the active period. And, it may or may not be any meetings during the break, but there will be a schedule put together for the spring semester. Most likely it will be same day, same time, unless there will be protests against it. Okay. Another thing as a little favor, if you have young colleagues and friends who hasn't taken computational chemistry, suggest them to consider this course, because it will be it can be cancelled if there is a specific number of attendees accumulated.
Are you currently under enrolled?
Yes.
By how many?
Huh?
Sorry.
Yesterday by 7. Okay, then wishing everyone a happy holiday period. Stay tuned for any news, and if quick personal chat is needed, I'll stay here for a long time.